Today we commence our last discussion on the subject of sampling, and we look at the question of aliasing once again, but from various perspectives. In the previous lecture we introduced the idea of aliasing, and we essentially brought out the concept of aliasing by looking at a single sine wave. Okay. Now today we take this discussion further. The first thing that we do is to look at aliasing outside the context of the Fourier domain. All right. So we look at it from a very common everyday experience, or from a set of everyday instruments that we see all around us as electrical engineers, or just as simple people. So let's begin with the simple people part. Let's begin with a simple cycle wheel, right? Now let's visualize this. Forgive my circular drawing, it's not circular, but it conveys the idea. Visualize this to be a cycle wheel, and let me mark the spokes on the wheel. All right. So you can visualize spokes like this, and I'm not drawing the spokes, I'm just indicating that there are spokes here, and let's number them. So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16. It doesn't matter how many. My intention is just to use this idea of a cycle wheel to illustrate the principle of aliasing if we see it in everyday life, right? Now let's visualize that the cycle wheel rotates with the movement of the cycle, right? And typically, as is the case with our vision system, we focus our attention on one point in space, in static space, right? So for example, even though the wheel might rotate, right, we typically focus our attention on one part of the wheel. So for example, it could be this part with relative to the rest of the body of the cycle, right? So suppose the cycle wheel rotates in this direction. The sequence of numbers, I mean, if you could think of this, the cycle spokes as being numbered, then the sequence of numbers that I would see is 1, 2, 3, 4 and so on, if the wheel rotates very slowly, right? If the wheel rotates very slowly in this direction, I would see the numbers 1, 2, 3, 4 in sequence, right? Now here I am assuming that the rotation is so slow that one can actually see each spoke as it moves. As the rotation becomes a little faster, the situation is that we see, let's say, 1 followed by 3, then followed by 5, 7, 9, every alternate spoke, let's say, right? So we start missing spokes, right? One must remember that when we are talking about speeds of rotation, of the order of that of a vehicle, then it's unlikely that our eye really focuses on the complete, when the idea of continuity gets lost. Our vision is not always continuous, right? We tend to see discrete chunks. So in fact, our visual system very often carries out sampling without our realizing it, all right? So as the wheel rotates a little faster, we see the pattern 1, 3, 5, 7, 9, 11, 13, 15 and so on, right? A little faster, and we see the pattern 1, 4, 7, 10, 13, 16, 19 and so on and so forth. And one can visualize this process going faster and faster. So there comes a point when you see 1 followed straight away by 11, when the wheel rotates fast enough. So you see the pattern 1, 11, 1, 11, 1, 11, all right? And that's the place where confusion just begins. Confusion of what kind? Well, whether the wheel rotates in this direction. Now here I have shown it rotating in the clockwise direction, right. Were it to rotate in the anti-clockwise direction at the same speed, I would still see the pattern 111, 111. Alright, so that comes as a point of confusion, where the visual system is not clear whether the wheel is rotating in the clockwise direction or in the anti-clockwise direction. Now visualize the wheel rotating a little faster. So what does one see? One sees the pattern 1 followed by some number on this side. So let us say, for example, one might see the number 1 followed by the number 13. And after that will be some other number. Again, you see, visualize, you are going through more than half a cycle, right. So you see the number 1 followed by 13, and then again you go through more than half a cycle, right, and perhaps see a number farther and so on. So now what is the situation at this point? You see, at this point, so what would happen? I mean, you might see, you should have seen, I mean, if the wheel is rotating like this, or rather putting it the other way, your eye would tend to believe the wheel is rotating in this direction if you see a sequence of numbers which are close enough to one another in this direction. So if the wheel is rotating like this, you would expect, your eye would expect to see a sequence of numbers that are close in this direction, right. So if for example, if you see the numbers 1, 3, 5, 7, your eye or your visual system seems to interpret the wheel to be rotating in this direction because the numbers are closer here. On the other hand, if the wheel were rotating in this direction, you would tend to see the numbers 1 and slowly, if the wheel were rotating in this direction and slowly, you would tend to see the numbers 1, 20, 18, 16 and so on. So conversely, if you saw the numbers 1, 20, 18 and 16 and so on in pattern, sequence, you would tend to interpret it as if the wheel were rotating in that direction and of course with a reasonable speed. So the interpretation of our visual system often depends on the simplest possibility that could lead to the situation being seen, right. And actually this is an example of aliasing. Now when the wheel rotates very fast, what happens? You see a pattern like this, you see 1 followed by 13, then skip another whole half cycle and come somewhere here, right. So you see a pattern 1, 13, some number here and so on, which to your eye appears to be a situation where the wheel is rotating in this direction and therefore producing the pattern 1 followed by 13 followed by some number here and so on and so forth, right. So when the speed of the wheel goes beyond a certain value, the visual system, which focuses its attention on one point on the static plane, interprets or rather misinterprets the wheel to be rotating in the opposite direction. In fact, I am sure a lot of you may have seen this in visuals or in cinematic, television, but you may not have interpreted it in this context. For example, when racing motorbike, it appears that the wheel rotates in the direction opposite to, and the reason for that essentially is this phenomenon here. Of course, it is not entirely the visual system, it is also the camera behind the camera at times, and that sampling rate might fall short of what is recommended by the Nyquist principle, and therefore the wheel might appear to rotate in a direction opposite to its actual direction of rotation, and what is more, with a less speed, with a smaller speed. Yeah. So there are two things that deceive: the speed and the direction, as we saw last time with the example of a sine wave when we looked in the spectral domain. Now the same phenomenon can be seen in a fan. Observe the motion of a fan in a room, increasing its speed from a very low speed to a high speed. initially you feel the fan rotates in the correct direction when it rotates slowly. As you increase the speed of the fan, there comes a point where it seems static. And beyond that, it appears that the fan rotates in the opposite direction and very slowly. The blades seem to be rotating in the opposite direction. Take a minute next time to observe a fan that rotates very fast and link this idea to the phenomenon of aliasing. Alright, so this is another manifestation of the principle of aliasing. Aliasing, therefore, is normally a cause of misinterpretation. But today, we shall also see that aliasing has certain positive effects, or rather, aliasing can be used or can be exploited to do certain things that we wish to do either in the domain of communications or in the domain of instrumentation. Let us begin with the domain of instrumentation. Let us take a very simple example. Now we wish to display a waveform on an oscilloscope. I have shown here 3 periods of a waveform that I wish to display on an oscilloscope. Okay. I am assuming that the period t is extremely small, and because of that, the frequency of the waveform is so large that the oscilloscope and its components do not respond to it satisfactorily. Well, a lot of you might, I assume that a lot of you might have worked with an oscilloscope. You may not have been exposed to all the possibilities in an oscilloscope, one of which might be what I am going to discuss today, but you must have seen how an oscilloscope displays waveforms, right? And although you may not fully understand why, you might also be aware that there is a certain range of frequencies within which the oscilloscope displays waveforms satisfactorily. That is called the bandwidth. In fact, the bandwidth of the oscilloscope is one of the most important quality factors in the oscilloscope. By quality factor, I mean something that determines the quality and therefore the cost. So normally a costly oscilloscope is one also which has a large bandwidth, in addition of course to robustness or other facilities like multiple channels and so on, right? But often the cost of an oscilloscope is closely linked to the bandwidth in which it can operate. So for example, for radio frequency communication, if one requires to display radio frequencies, some of which can go even into the range of gigahertz, one would require an extremely sophisticated oscilloscope. In the laboratory, one often makes use of oscilloscopes which do not go beyond a few hundreds of megahertz at most, right? They do not really transcend range of, and that is because a lot of components that we use in an oscilloscope are discrete components, and discrete components do not work beyond the range of a few hundreds of megahertz, in fact maybe not a few tens of megahertz at times. Now the reason why I brought this issue up is, one can exploit the idea of sampling to take the oscilloscope to capabilities beyond what its bandwidth can offer, and the idea is very simple. Let us assume that this periodic waveform, of which I have shown 3 periods, has a frequency well beyond the bandwidth of the oscilloscope, let us say a frequency of a few gigahertz, right? Can we still display this waveform on an oscilloscope, albeit deceptively, right, by aliasing? So here we shall bring out a positive effect of aliasing. Now the idea is very simple. Let us assume that we have an oscilloscope which can sample the waveform and interpolate between samples. We have already been exposed to the idea of interpolation, haven't we? I mean, we discussed that the method of reconstruction of the waveform from its samples is essentially a method of interpolation. We use the sin x by x pattern to interpolate. And of course, we shall also discuss later that although the sin x by x pattern is an idealistic pattern, one might use simpler patterns with the expense of inaccuracy, right? Anyway, coming back to this, let us assume first that we could use an ideal interpolator, in which case we could take samples of this. But naturally, if we were to obey the Nyquist principle, then our sample should be taken at more than twice the frequency that this waveform has, which is inordinately large. So, from the frying pan into the fire, where we try to construct an oscilloscope, display fast waveforms, we are now asking for a sample. We can sample at even higher than the frequency being actually displayed. So, that would not work. So, instead, let us do the following. Let us take one sample here. The next sample, not here, but here. That means at a distance delta away from the beginning of the period. The next sample shall be taken. So, the sampling period here becomes t plus delta. And we assume here for the moment that delta by t is 1 by n, where n is an integer. So, delta is a fraction of the form 1 by n, it is 1/nth. Yeah. So, where would the next sample come? It would come at 2t plus 2 delta, right, somewhere here. And now you can visualize this being taken further. So, in n periods of the waveform, we are collecting n samples, or rather, is it n periods or n plus 1? Plus 1. So, in n plus 1 periods of the waveform, because when you go to the nth sample, you have covered nt delta, which is t. So, you have gone to n plus 1 t, right. So, in n plus 1 periods of the waveform, you have collected n plus 1 samples of a period. So, it is as if you have collected the following points on the period. You could draw this period here, and let us take as an example n equal to 5. So, in which case I shall divide this into 5 equal intervals. And here I have this sample, say this sample here, the sample here, the sample here, and the sample here. All right. Now, this is what the oscilloscope takes, and then it can use an interpolation mechanism to join these smoothly. I mean, that is not difficult to visualize. How we do it, we shall not bother at the moment, but one can visualize it's some kind of a low pass operation or some kind of a smoothing operation, right, would give us a smooth waveform joining these points, which would closely resemble one period of the original waveform. So, now instead of trying to sample at the Nyquist rate, I have actually brought the sampling rate down, so that I take n samples over n plus 1 periods, less than one sample in a period. In fact, I can take this idea further. Here I have skipped effectively one period between samples, right. So, I have taken a sample at 0 and then a sample at t plus delta. But if my waveform has a frequency even higher, I could take the next sample at 2t plus delta. So, I could make my interval 2t plus delta, where delta by t is 1 by n, right. And then I would skip 10 plus 1 periods to obtain the set of n samples, right. So, I could skip, so I could keep on getting the same pattern at higher and higher frequencies if I am willing to skip multiple periods. Now, what am I doing effectively here? Effectively, I am using aliasing. What have I done? I have taken the original waveform, which is at a much higher frequency. I have undersampled it, that means sampled it at well below the Nyquist rate, right? And I have reconstructed what looks like the original waveform. That is what aliasing means, what looks like the original waveform from its samples. So, here aliasing has actually served a useful purpose for me, and this principle is the principle of what is called the sampling oscilloscope. The sampling oscilloscope is a version of a digital oscilloscope which can allow you to display waveforms of very high frequency, without actually sampling them at Nyquist rate, right. And the principle is based on a clever use of aliasing. Yeah. Yes, Nikhil.
So, periodicity is essential, right?
The question is periodicity essential? Yes, indeed. Not only is periodicity essential in this context, it is also essential to make sure that your sampling interval has this rational relation with a period. That means the sampling interval divided by the period of the waveform must be a rational number. That is also essential, right.
That doesn't happen, what do you get?
Yes. Now, in fact, here it is also, that means that it is also important to know a priori about the possible frequency, or it also means that there is some prior adjustment that needs to be done before a satisfactory display is obtained, right. See, the sampling interval is in your hand, but matching the sampling interval to the waveform that is coming in needs adjustment. So, in fact, you have to allow flexibility in the sampling interval here, because without that you will not be able to match the frequency that you are trying to display and the sampling interval, right. You can see that the ratio needs to be rational. The sampling interval divided by the sampling period needs to be a rational number here, right. That is the most general requirement, and that needs to be done by adjustment. Yeah, we do not know the incoming signal frequency here, but that is why an adjustment is needed. See, for example, even when we use the oscilloscope in normal mode for low frequencies, we do not know the frequency of the incoming signal all the time, but we need to use the controls very often, the controls of auto, normal and so on, right. So, I assume that you might have actually used an oscilloscope and used some of its controls, the triggering control, the auto, the normal and so on, right. And all these controls are required for the same kinds of adjustment. So, in fact, a lot of times we derive a triggering signal for the display of the waveform from the incoming signal. In an oscilloscope, very often the triggering signal that is used to display the waveform is derived from the incoming signal. Now, here we might need to do something similar. We might need to bring out a triggering signal, but we may not be able to use that triggering signal directly for display, but to get an estimate of the period. And based on that estimate, one may then have to correct one's sampling interval so that its ratio with the period is rational. Because you require adjustment with a normal oscilloscope to display waveforms, you need adjustment with this oscilloscope to display waveforms that are of course periodic. And of course, periodicity is essential, as is the case with oscilloscopes otherwise. Periodicity is essential for steady display on an oscilloscope, right. So, this was the first example of a positive effect of aliasing. Let us look at one other. You see, one way to interpret aliasing is the following. If we recall, we had talked about modulation earlier, right? We talked about modulation. What did we achieve in the context of modulation? We translated a given waveform, its spectrum, to a frequency different from its original frequency range. That is what modulation did. How did we achieve it? We achieved it by multiplication with a carrier. Now, at that time we made use of a sine wave carrier. But suppose we do not have a sine wave carrier, right. So, suppose we have a square wave carrier, which might be easier to generate at times. Actually, what I mean by a square wave carrier is a gating pattern. This is what I mean by a square wave carrier or a gating pattern. What is a gating pattern? A gating pattern is a waveform that either passes the incoming waveform as it is, or passes it inverted, or does not pass it at all. So, here in this subinterval it passes the waveform as it is. In this subinterval it passes the waveform inverted. And of course, here there is no region where it does not pass the waveform at all, but suppose this waveform were to be 0 in some interval, then that is the place where the waveform would be blocked. So, either block or pass it as it is or pass it inverted. That is what a gating pattern does. Now, it is often much easier to construct a circuit that can cause gating rather than actually multiply a message signal or a signal that we wish to transmit by modulation with a sine wave. That is much more complicated. Multiplying a message signal with a sine wave in hardware can be a complicated operation. So, instead it could be easier to construct a circuit out of diodes for gating. In fact, even at your exposure you might be able to construct a circuit with diodes. I encourage you to think about it. Construct a circuit with diodes which can cause this kind of a gating operation. Right. Anyway, so suppose we happen to multiply our incoming waveform. Let us say the waveform is xt with this, let us call this pt, let us call this gating pattern pt, right. So, we multiply xt by pt. Now, let us assume that xt is band limited. And let us assume that the frequency of Pt, namely 1 by Tc, is much larger than twice the maximum frequency component in the waveform xt, right. So, you see, if Pt is periodic with a period Tc, the product waveform xpt here is going to have a spectrum given by the convolution of xt with the spectrum of pt. And what is the spectrum of pt? It is a train of impulses located at all multiples of 1 by tc, which we shall call fc. So, pt is periodic with frequency Fc. Yeah. So what kind of a spectrum does XPT have? Well, let's sketch it. Let's assume the spectrum of XT, which is XF, is this prototype spectrum, just for illustration. FM minus FM. Okay. I have explained to you before why we use this as a prototype spectrum to illustrate the idea, because it's the simplest spectrum which has a different value at every point, right? Now, this prototype spectrum is translated by every multiple of Fc, and these translates are added after being scaled by the Fourier series coefficients. So, here we have C0 Xf at 0 frequency, C1 Xf minus Fc at the frequency Fc, C minus 1 Xf plus Fc at the frequency minus Fc, and so on. And you can continue this further to 2Fc, 3Fc, and so on and so forth. Is that correct? Yeah? Now, if our intention were to replicate the original waveform xt, we would have put a low pass filter with a cutoff of Fc by 2, right. So, had we put a filter with a cutoff of Fc by 2, we would have got back C0 times Xf or some multiple of Xf, right, and from that we could have reconstructed the waveform Xf, Xt. But now we can exploit the phenomenon of aliasing. So, instead of putting a low pass filter, we could now put a band pass filter around the multiple of the carrier that we want. So, suppose we want the carrier frequency to be 3 times Fc. So, suppose I want a carrier frequency of 3 megahertz, right, but I have a gating pattern only of frequency 1 megahertz. Then here in this process I have already created a replica of the spectrum at 3 times Fc. So, I could put a band pass filter with a pass band from 3 Fc minus Fm to 3 Fc plus Fm. Yeah, I could put a band pass filter with a cutoff with a pass band between 3 Fc minus Fm to 3 Fc plus Fm. And recall that if my original since my original gating pattern is a real function, C3 and C minus 3 would be complex conjugates. So, when I put a band pass filter symmetrically on both sides of the frequency axis, the spectrum would also remain conjugate symmetric. So, it would indeed give me the modulation of the original waveform xt with a carrier of frequency 3 times Fc. In fact, the same principle can be extended to get a carrier which is any multiple of Fc. So, there are two advantages that we have gained here. One is that I have not needed to multiply explicitly with a sine wave. So, I have not needed to generate a sine wave at all, which cannot always be done very easily. Generation of a sine wave requires construction of an accurate oscillator. So, here it illustrates that you do not need to construct the oscillator very accurately. In fact, you can have a very crude oscillator. You do not even need to have an oscillator. You could just have a gating pattern which can be built out of diodes. In fact, this is the principle of what is called the ring modulator in communication. This is the principle of the ring modulator. in communication. Right? The second advantage here is that I don't really need to construct a waveform of frequency equal to the carrier frequency, but it could be sub-multiple. So, even if I want a carrier at 3 megahertz, I could construct a periodic waveform of period of frequency 1 megahertz. And if I have a Fourier component at 3, I need to ensure that I have a Fourier component at 3 times Fc. If I have a Fourier component at 3 Fc, then replica of the spectrum appropriately shifted occurs at 3 Fc and minus 3 Fc, and that can be extracted as the modulated version of this signal with a carrier frequency of 3 times Fc. Two advantages result when we exploit aliasing. So, aliasing can actually be exploited to the advantage of the engineer. All right. In fact, I shall take this now from a converse perspective. You see, here what have we done? Here what have we done? We have made use of the fact that aliasing can take us from a low pass to a band pass signal, or we have been able to exploit aliasing to shift the band of the signal in question. Well, where are we using aliasing here? All these spectra are called aliased spectra. All these are called aliased spectra. You see, why are they called aliased spectra? Because they were not really there. They are false replicas or false apparitions of the original spectrum that have emerged as a consequence of sampling. That's a broader way to understand aliasing. What is, see, in a certain sense, what we are doing is to create a false version of the original signal, because there are false replicas created. These additional spectral components are false, or those spectral components are not really present in the original waveform. They have been created as a consequence of sampling. And in the reconstruction process, you are intentionally retaining the false ones and giving up the true ones. That's why we are calling this aliasing, right? We are forcibly introducing aliasing.
The waveform shape also changing.
So the waveform shape, of course, would change. It would, in fact, it would amount when, if you, for example, if you made a band pass filter around 3 Fc, it would be equivalent to multiplying the original waveform by a sine wave of frequency 3 times Fc, right?
The gated signal comes in.
Yeah, the question is, how does a gated signal come in? The gated signal is a periodic signal with period Fc. So, in fact, any periodic signal with period Fc would do. But the simplest, you see, we are trying to construct a very simple periodic signal with period Fc. What can be the simplest possible periodic pattern? Something that is constant for some time and again constant for the remaining time. And this can be constructed very easily with a circuit which either passes the waveform as it is or inverts the waveform. Right? So, this is called a gating pattern. Now, you could make this gating pattern periodic with a period that you desire, right? So, gating pattern is something which you can construct without multiplications in hardware. You could simply construct it by allowing the waveform to pass as it is or allowing it to pass inverted. This kind of an arrangement can be made with diodes. Well, some of you may have been exposed to the idea of a full wave rectifier. What does a full wave rectifier do? It passes the sine wave as it is for half the cycle and inverts it for half the cycle. Let's say that's an example of gating. So, if you do something like that here, but at a much higher rate, right, at a rate of Fc, then you could effectively achieve multiplication of the original periodic pattern, which amounts to the spectral domain to creating false replica spectrum, and you are retaining a false replica and throwing away the true one. That's why we are calling it aliasing, and we are doing that to advantage to create a modulator. Yeah. So, now coming back to this issue here, what we have done is to take a signal which was originally in a low frequency range, right, and translate it into a high frequency range as a consequence of aliasing. Now, we shall make use of the same idea to see if we can relax the Nyquist principle in a situation where the signal does not occupy the whole band up to its maximum frequency component. Let me take an example. So, here I am assuming that I have a spectrum that looks like this. Let me take some arbitrary, FW and 2FW. Some arbitrary FW and 2FW, right? And let me have a spectrum which lies in between them. So, let me have a spectrum like this, strictly in between. Of course, this is a real signal, xt with spectrum xf, and this is xf. What I have shown here is xf. And of course, we assume that xt is real. So, xf is conjugate symmetric, as is always the case in our discussion before this. Now, at this point, a little aside. If you look carefully, the reason why we get the requirement of 2 times Fm is because the signal is real, and actually on the frequency axis it occupies a range of 2 Fm, from minus Fm to plus Fm, right. Now, we might be tempted into asking the following question. Suppose I have a complex signal, whatever it might mean, then I don't have conjugate symmetry. So, it is quite possible that I might have a spectrum of 2 Fm on the negative frequency side. Can I get away by sampling at 2 times F? You see, at 2 times Fm, can I sample at F? Well, indeed I can, because the original spectrum would get translated by every multiple of Fm, and these translates would be non-overlapping. Now, as I said, this is deceptive. This is deceptive because every sample that you take is a complex number. So, actually you have 2 real numbers being taken at every sampling point. So, all that you are doing is, initially you were taking 1 real number at twice the rate, here you are taking 2 real numbers at half the rate. Right. So, there is really no advantage in that sense, right. Of course, this is just a little aside that I have mentioned. However, this fact can be exploited in some situations, right. One can, if it is convenient to store 2 real numbers at a time, one can actually make use of what is called a complex envelope to a signal and sample it on that basis. Anyway, coming back to this discussion here. Now, let us assume the spectrum looks like this. So, the spectrum is non-zero strictly between Fw and T. Right, and I have intentionally kept the spectrum non-zero to within a range here inside. So, there is a little gap just to be on the safe side. Now, let us assume, so let us think of this spectrum as being non-zero strictly between Fw and 2Fw. We do not mind which region in between Fw and 2Fw, but it definitely does not go below Fw and does not go above 2Fw, right. Now, if we went blindly by the Nyquist principle, what would be the sampling rate required? 4 times Fw, because the maximum frequency component could be 2 Fw. So, we would expect that you need a sampling rate of 4 Fw. Now, what we would like to make use bandwidth, that means a region of the spectrum in which the region of the frequency axis in which the spectrum is non-zero. So, can we make use of the bandwidth instead of the highest in determining the sampling rate? So, let us ask a specific question. Suppose I mistook the bandwidth for the highest frequency component. So, suppose bandwidth here is FW, as you can see. So, suppose I tried to sample this waveform at 2 times the bandwidth instead of 2 times the highest frequency component. So, I sample this at 2 times FW. What would happen? So, let's construct the spectrum. So, suppose we sample xt at a sampling rate Fs equal to 2 Fw, not 4 Fw. Okay? Let us construct the spectrum. All right. Now, the original spectrum as it is, and what happens when you sample at a rate equal to 2 Fw, the original spectrum is taken, translated by every multiple of 2 Fw, and these translates are added. Let us assume that the sampling waveform is an ideal impulse train, in which case all the translated versions of the spectrum have the same height. Yeah, so let's translate this forward first by all multiples of 2 Fw. So when you translate this by, so let's call this part of the spectrum A and let's call this part of the spectrum B. Okay. So when we translate this forward, what happens? This B comes to 0 first, and we'll keep marking crosses on top to denote the aliased versions. All the others are aliased versions of the spectrum. So, B here, another B here, sorry, let us put the B inside, and another B here, and so on. And so on and so forth. And of course, backwards as well. So, there is another B here. So, you can keep drawing the B's. What about the A's? The A's also get shifted backward and forward by every multiple of 2 Fw. So, when the A gets shifted backwards, there is an A here. There is another A here. And so on and so forth, and forward. So, of course, the original A is here. So, forward means there will be an A here, and so on and so forth here. All right. So, it is a very interesting situation. Yeah, do you see what I am getting at? Now you see, as a consequence of aliasing, we have created all the crossed spectra that I have shown. But none of those cross spectra interfere with the original spectrum. So, can we reconstruct the original spectrum? Certainly, but by what mechanism? By using a band pass filter instead of a low pass filter. So, suppose I put a band pass filter. With a pass band from Fw to 2 Fw. Yeah. Suppose I put a band pass filter with a pass band from FW to 2FW. It retains these A and B, which are the original spectrum, and throws out everything else, right? So, we have been able to sample the signal at what is effectively half the Nyquist rate. In fact, at twice the band width rather than twice the maximum frequency component, and yet retrieve the original signal, right. So, this is an example of the converse situation to what I discussed earlier. You see, you can allow aliasing to occur or aliased versions of the spectrum to fall in an unoccupied band. That is the idea being used here. This is an unoccupied band. So, you do not mind if aliased versions fall there, because you can filter them out afterwards if you know the original band is unoccupied. Now, this is an example of what is called band pass sampling. Now, one must not be deceived into thinking that we have been able to achieve what we want for all band pass signals. In fact, we need to probe what we have got a little further. You see, here we assume that we sampled exactly at 2FW. Now, suppose we happen to sample, whether fortunately or unfortunately, at a little more than 2F plus W, right, than 2F plus W. What would happen? This B which moves here would move a little backward, right. In fact, it might, in the worst situation, if it comes, B's come here. Now, instead of 2FW, if you happen to sample it at 3FW or even 3FW plus delta, you would actually have this B which came here coming somewhere here. And similar thing would happen to the A, right. So, the A which came here, right, this was, so of course I am talking about, actually I am talking about A, isn't it. So, A which came, you see, so it should have come here, it could have come here. So, you see, what I wanted is it comes here, and if it, alright. So, suppose you sample it, even, in fact, even 2FW plus delta is bad, right, 2FW plus delta is bad. Now, look at this, you see, you have A, it comes here, and you sample exactly at 2FW. But if you sample at a little more than 2FW, this would move backwards and it would come into this. Right. So, this A which was now not falling into the original spectral region interferes with the region minus 2FW plus 2FW to minus FW, even if the sampling rate is just a little more than 2FW. Now, you see, having it more could seem to be an advantage. I mean, if you looked at the case of the Nyquist sampling theorem originally, once you go beyond the Nyquist rate, you are never at a loss. So, if your maximum frequency component is FM, no matter how large your sampling rate beyond 2 FM, there is no harm done, right, whereas here there is harm done. Now, the same thing can be argued if the sampling rate is a little less than 2FW, right. What will happen if the sampling rate is a little less than 2FW, right. You can also show, I leave it to you to show, that if the sampling rate is a little less than 2FW, you will still have trouble spectrally. So, what does it mean? It means there is a tolerance, and where is that, actually there is no tolerance. You know, if the spectrum, if this A were to occupy the entire range from FW to 2FW, there is no tolerance at all. Either you have precise 2FW sampling, in which case you can reconstruct the signal with band pass filtering, or a little bit this side or a little bit that side, and you have aliasing. That's the problem. So if you wish to carry, yes, Samir?
So do we need to find some FW such that it lies in FW?
Ask the question properly. Yeah.
So do we need to find some FW such that your entire spectrum lies in FW and 2FW, or is it sufficient to find some F start and F end where it just fits in, where Fn need not be exactly twice F start?
Okay, good question. Let me repeat the question. Let me also reinterpret the question for the class. Well, the question is, do I need to fit the spectrum? Do I need to choose my, see, actually here if you look carefully, W are a choice. Why am I saying it's a matter of, they are a matter of choice? Because they are not really the spectral ends. The spectral ends are not in your control. But the points at which you put FW and 2FW is in your control. So, what this indicates, what this problem of, inaccuracy of sampling rate indicates, is that normally it would be desirable to choose an FW in such a way that you have a gap on both sides. So that you fit your spectrum not exactly between FW and 2FW, but well in between or within. So actually it is this gap that allows you some tolerance. So that gap is left there intentionally. You have chosen FW and 2FW in such a way that you have a gap. And then if you sample at 2FW plus or minus a little delta, you still have some tolerance. You can see here, suppose you sample at more than 2FW, this will come not here but a little bit inside. But if it comes a little bit inside, it's fine because you still have a gap here. So I can make my band pass filter not strictly between minus 2FW and 2FW, but I could bring it a little closer to the spectral ends. Yes, Nikhil, yeah.
So that means there's some band pass signals cannot be, you cannot use the same method for some.
All right. So now there are questions that arise from this discussion. Right? There are what I need to uncover a host of possibilities. Right? The first question, as Nikhil says, is, does it mean that there are some signals for which I cannot carry sampling? Right? Well, I shall not answer all the questions at this point. It's a very subject. What I have done is only to open up the subject to you. Right? To open up the possibility that one can carry out band pass sampling, but it is a very case to case kind of operation.
Do you need 2FW, NFW?
Well, in fact, here one of the generalizations that one can make is that you don't really need to have it between FW and 2FW. It could be two integer multiples of some FW. So it could be between some 4 and 5 FW, if you please. Right? And one can still work out a sampling principle for that. So one can have a whole host of sampling theorems or sampling approaches based on different ways of looking at the same spectrum. Right? In fact, one can do very peculiar things, like divide the spectrum into parts and sample each of them separately. Right? So what I have done here in this example is only to open up for you a whole host of other possibilities that arise from the possibility of band pass sampling. Right? But if you look at some of the journals in the area of signal processing or in the area of communications, you will realize that the question of sampling is a very well researched question and a non-trivial question. What we have done in the past few lectures is to lay a basic foundation to the ideas of sampling. But there is a very wide scope of possibilities in sampling depending on the a priori information that one has. That's exactly what I am saying here. In fact, we began the whole discussion of sampling by emphasizing that the requirements on sampling depend on the a priori information that you have. For example, if you know a priori that your signal is a sine wave of frequency 50 hertz with an amplitude of 2 volts and a phase of 0, you don't need to sample at all, right? That's an extreme case. Or if you know a priori that my signal is an exponentially decaying pattern with a decay time constant of 2 units of time, whatever they might be, you don't need to sample at all. Indirectly, what we've been doing here in this last few minutes is to introduce a little more a priori information and therefore reduce the amount of sampling. If you think about it from that perspective, there is a broader philosophy. If you put in a little more a priori information, you can use that cleverly to reduce the requirement on sampling. That can be taken further, and at this point, as far as sampling goes, with a caveat, with a statement that if it is only band limitedness that we are assured of, then the Nyquist principle says you must sample the signal at least twice the maximum frequency component. But if you have a little more than band limitedness, for example, if you also know the signal is band pass, then that a priori information can be exploited. Now you can ways, right? And what is the best approach once you have a certain amount of a priori information is a deep question in itself. That amounts to asking me, how much a priori, can I quantify the a priori information that I have? If so, can I use that, can I quantify what should be my minimum sampling rate with so much of a priori information? Very deep questions. One cannot answer them at this stage, right? But I leave it in your mind for you to look further, right? All right, with this we close our discussion of aliasing, right? In the next lecture, we shall look at some alternatives to interpolation, right? We close our discussion of sampling, but we look at some alternatives to interpolation as practical alternatives to the idea of sin x by x kind of interpolation. Thank you.